Hello all, we are finishing up chapter 9, so chemical bonding 1, basic concepts. This next topic we're going through is writing the Lewis structures for a molecule that has resonance. So to go more into this topic, let's define what resonance is and what resonance structures look like. A resonance structure is one of two or more Lewis structures for a single molecule that cannot be represented accurately by just one Lewis structure. So ozone is O3. As a molecule of ozone O3, this can be represented by this Lewis structure as well as this Lewis structure. You'll notice these look very similar. They're sort of reflections of one another. So this Lewis structure is, quote, in resonance with this representation of this Lewis structure. So if we covered this one up and we just looked at this one does not accurately represent a molecule of ozone. Instead, this is an accurate Lewis structure, but this is an accurate Lewis structure as well. So first the double bond between these two O's, then the double bond between these two O's, negative formal charge, positive formal charge, negative formal charge, positive formal charge. One key factor that helps us know if there might be a structure with resonance is if we have a double or triple bond. If a structure has a double or triple bond, it might have a structure that has resonance because we could flip that double bond to the other spot. If a molecule only has single bonds between the atoms, we can't have resonance if a molecule only has single bonds. So resonance, 2 different or 3 different or more different Lewis dot structures that do accurately represent that molecule. We show 2 Lewis dot structures having resonance by this double-headed arrow, which means that this structure is in resonance with this structure. So let's try this practice problem and see if this molecule of ethylene C2H4, let's see if it has resonance by drawing the different possible Lewis dot structures. If there's just one possible Lewis dot structure, then we don't have resonance. It's also important that if we do show resonance structures, that those structures also have to satisfy the same rules we talked about for Lewis dot structures. So resonance structures also have to satisfy the octet rule. If they don't, then they really aren't viable resonance structures. So for viable Lewis dot structures, we know the goal is to have a satisfied octet or duet. So if we're trying to draw a resonance structure that doesn't satisfy that, then it probably isn't a resonance structure. So again, as mentioned, resonance structures must satisfy all the usual requirements of a correct Lewis structure. For ozone, this is a correct structure and this one as well. All we're doing is switching the placement of that double bond. These two are both okay because they both satisfy the octet rule. Going back up to these representations because they're a little cleaner to work with, let's show why the octet rule is satisfied for all the oxygens here in these two structures. So in resonance structure on the left, we have 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. Then 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. Then 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. So all 3 of these oxygens have a satisfied octet. This is a viable resonance structure. We can do the same thing to this one and prove that. It's also the reflection of this one. So we'll know that these oxygens also all have satisfied octets. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is a viable resonance structure. This is a viable resonance structure. They are different because this double bond is between these two and this one, whereas the double bond is between these two in this structure. This is a different oxygen atom than this one, so these are indeed different structures. We know we could draw other unreasonable Lewis dot structures that don't have a complete octet, they don't have the correct number of electrons, different things like that. What if we're thinking, well, we have a double bond and a single bond, double bond and single bond. What about two double bonds between the oxygens? Why can't that be a resonance structure as well for ozone or O3? Well, one thing we would need to do first for drawing a Lewis dot structure for ozone is to count the number of valence electrons we can use in the structure. Oxygen has 6 valence electrons. There are 3 of the oxygens. That means we have 18 electrons to work with within a Lewis dot structure. Remember, for Lewis dot structures, we're just counting the valence electrons. Looking at the periodic table and knowing how many valence electrons our S and P block elements have is going to be really, really important moving forward with Lewis dot structures. So in these two, how many electrons are we using? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that is correct. As another reminder again, remember each bond contains 2 electrons, one from this atom, one from this atom. A double bond then, that does contain 4 electrons. So 1 bond, 2 electrons, another bond, 2 more electrons, 4 electrons total within this entire double bond. Let's see what's going on with this one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We haven't used all 18 electrons that we need to use for O3, so this is incorrect. If you're thinking, well, couldn't we just put on a lone pair maybe on this one? Well, what would that do to this central oxygen's octet rule? 2 double bonds, that's 4 electrons. 2 more double bonds, that's 4 more electrons. When we add on a lone pair like this to the central oxygen, that's now causing the central oxygen to have 10 valence electrons around it. That disobeys its octet rule. This is not a good structure. Even if we added on a lone pair here, that causes the central oxygen to have 10 electrons around it. That goes against the octet rule, so this is not a good structure. Then, well, maybe we could just use all single bonds. If we use all single bonds between the 3 oxygen atoms, this central oxygen just has 1, 2, 3, 4 electrons around it. The octet rule isn't even close to being satisfied if we drew a structure like this, because this central oxygen again just has 1, 2, 3, 4 electrons around it. It wants to have 8. The oxygens on the side, 1, 2, 3, 4, 5, 6, 7, 8, those do have a satisfied octet rule. But overall, this is not a good structure. This is not considered a resonance structure for ozone. This one didn't have enough valence electrons. This one violates the octet rule. So we can't just draw any structure and think of that as a resonance structure. The resonance structures also have to have satisfied complete octets and use the correct number of valence electrons. They have to be viable Lewis dot structures. And so this important consideration I mentioned, a molecule or polyatomic ion can have resonance only if it has double or triple bonds. Molecules and ions with only single bonds cannot have resonance structures. So the way we think about resonance structures and how these Lewis dot structures relate to one another, we're sort of moving around that lone pair of electrons. So first it's in the double bond, and we know within each bond contains 2 electrons, so these 2 electrons within the bond can get pushed up to this outer right oxygen. At the same time, this lone pair then on the left oxygen can get placed into this spot to form a double bond. So this lone pair is escaping from the double bond and then going on to this oxygen, while this lone pair is going in to form a double bond. So that's how these resonance structures are sort of interrelated. It's a movement of those lone pairs of electrons to be lone pairs, or then to move in to then form a double bond. So this movement of electrons is how we establish resonance for different molecules. That means we need to find just one reasonable Lewis dot structure, and from there we can move around the double bond to see if we can establish resonance. So we'll move around the lone pairs and the double or triple bonds to see what structures can exist that can be resonant structures. And so another key point with resonance is that resonant structures differ only in how the double or triple bonds and lone pairs are arranged. They never differ in which atoms are bonded to which. So for instance, hydrogen, carbon, then nitrogen. If we completely change the order of the atoms to be hydrogen, nitrogen, then carbon, these are not resonant structures of one another. These are completely different molecules. So for resonance, the order of the atoms does not change. If the order of the atoms changes, we're looking at an entirely different molecule altogether. And so let's draw the Lewis dot structure for C2H4. One first step we should do is count the number of valence electrons in each atom. Carbon has 4 valence electrons, times 2 is 8. Hydrogen has 1 valence electrons, times 4 is 4. So 1 valence electron times the 4 hydrogens, that's 4. 4 plus 8, we have 12 electrons to work with. In drawing the skeleton for C2H4, we learned in the last part of chapter 9 that hydrogen will never be in the middle. That means that carbon has to be in the middle. So we can at least start with this. Then we also learned that carbon wants to form 4 bonds. In placing the hydrogens around these 2 carbons, we may think, okay, maybe 1, 2, 3. So then this carbon has 4 bonds around it. Then we'd try to put the other hydrogen here, perhaps. Let's see at least how many electrons we've used so far. We're definitely not done. We're just trying to see what this structure could look like. So far, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. That means we'd only have 2 more electrons to work with, and this carbon currently does not have a complete octet. So if we put 2 electrons here, this would still just be 1, 2, 3, 4, 5, 6. This is not a good structure for this carbon because it doesn't have a complete octet. So what we do, well, maybe we should move 1 hydrogen to the other carbon, and then let's see what that would look like. So instead, if we do this, what's happening with the number of electrons? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means we have 2 electrons left. These hydrogens, as is, have a happy duet because this electron and then they get to share this electron from carbon. These carbons, however, do not have a happy octet. They have 1, 2, 3, 4, 5, 6 valence electrons around their atoms. What do we do with these remaining 2 electrons then? Well, we might think, okay, I could put it here on this carbon. That would mean 1, 2, 3, 4, 5, 6, 7, 8. This carbon would have a happy octet, but this one is still missing a happy octet. To satisfy this carbon's octet as well as this carbon's octet, we should move this lone pair in to form a double bond. What that ends up looking like is something like this. We have a double bond here, then hydrogen, hydrogen, and 2 more. This also works for the 2 carbons because now they have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. These both have happy complete octets. Also to point out again, for carbon, it likes to have 4 bonds around it. Right now it has 1, 2, then 3, 4. So this is another way for carbon to have 4 bonds around it. It has a double bond and then 2 single bonds. That's still 1, 2, 3, 4 bonds around carbon with its 1, 2, 3, 4 valence electrons it's coming in with. Carbon on its own has 4 valence electrons, so it likes to form 4 bonds. One of those bonds, or 2 of those bonds, I should say, can be a double bond. So here's 1, 2, 3, 4. Then for this one, 1, 2, 3, 4. Because we just showed that moving this double bond to maybe forming a lone pair here on this carbon doesn't work, because then that would leave one of the carbons without a happy octet. So we tried this. We tried moving electrons in the double bond to go on a different atom, and we saw that that would not be a viable Lewis dot structure. This means that this structure does not have resonance. We can't move the electrons in this double bond onto a different atom and still have every atom have a happy octet or a happy duet for the case of hydrogen. So no, we can't draw resonance because again, we can't move electrons in this double bond to another atom and still have a viable Lewis dot structure. Let's try a different one now, still in the same topic. So draw the Lewis dot structure for disulfur and monoxide, one of our molecular compounds, those prefixes di, and the prefix mono here for oxygen. Let's draw the Lewis dot structure and see what happens. One of the first things we should do is count the number of valence electrons. Oxygen has 6 valence electrons. Sulfur also has 6. 6 plus 12 then, we have 18 electrons to work with. For S2O, which one do we put in the middle? So now that we have the total number of valence electrons for S2O, the next step is to figure out which one do we put in the middle. There's a few different guidelines that were mentioned for what we put in the middle. We talked about previously that we could put the least electronegative atom in the middle, or we could also think about it as putting the unique atom in the middle. So which rule should we follow? Well, this one says that the least electronegative atom should fall in the middle. This rule takes priority over this rule. So the least electronegative atom, that's the one that should be in the middle here. What is less electronegative, sulfur or oxygen? Electronegativity increases going up the periodic table, so sulfur is less electronegative than oxygen. So sulfur is less electronegative than oxygen. So again, in deciding which one we put in the middle, think the least electronegative atom, try to follow that rule first. Then if needed, you can think about putting the unique atom in the middle, because clearly here, the unique atom, the atom that only shows up once compared to twice, is oxygen. But oxygen is more electronegative than sulfur, so the least electronegative rule, that follows first. This is the one we focus on first to then decide that, okay, then sulfur needs to go in the middle. That means we could put sulfur here and then oxygen here. As a reminder for these resonance structures, we can't change the order of bonding, otherwise that's an entirely different molecule. That means that doing something like this is not a possible resonance structure. The order has to be the same, and we again decided this order by putting the least electronegative atom in the middle. The least electronegative atom in the center. So let's proceed now and see how many electrons we've used up. We had 18, so far we've used 1, 2, 3, 4. Now that we have 14 electrons remaining, we can start to put lone pairs of electrons around the more electronegative atoms, or the ones that are on the outside. So for the more electronegative atom, we could start to put lone pairs then around oxygen. So 1, 2, 3, 4, 5, 6. We can't disobey its octet rule as we do this. So now we've added 1, 2, 3, 4, 5, 6. Now we have 8 electrons remaining. We would normally put those lone pairs of electrons around the outer atoms, which correspond to the ones that are more electronegative. Between this sulfur and this sulfur, one of them is not more electronegative than the other because they're the same atom. So then instead of thinking about the more electronegative one in this case, it's easier to think about adding those lone pairs to the outer atoms. So we have 8 electrons remaining. Let's start adding these on to the outer atom of sulfur. So this is now 1, 2, 3, 4, 5, 6. We've used up 6. We have 2 left. This sulfur now has a happy octet. Now with the remaining 2 electrons, we have no other choice but to then add those 2 to the central atom. So now we've used up the 18 electrons, but we have to check, do all of these have happy octets? Well, 1, 2, 3, 4, 5, 6, 7, 8. This sulfur, yes. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen, yes. This sulfur in the middle, however, 1, 2, 3, 4, 5, 6. This sulfur as is does not have a happy octet. To allow the central sulfur to have a happy octet, we should go ahead and try out resonance. How do we start to figure out resonance to have this central sulfur have a happy octet? Well, why don't we take a lone pair here and put it into a double bond? When we do that, the oxygen on the left is currently unchanged. Now we have a double bond, and then just 2 lone pairs of electrons remaining on this right-hand sulfur. So now the central sulfur, 1, 2, 3, 4, 5, 6, 7, 8, this central sulfur has a happy octet. Did we mess up this sulfur's octet by moving that lone pair into a double bond? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8. This sulfur still has a happy octet. This is a perfectly viable Lewis dot structure. We've used all 18 valence electrons, and each of our atoms has a happy octet. If you're wondering then, well, what about having moved this lone pair into form a double bond? Well, that is also a perfectly viable structure. Let's see what would happen. Double bond there, 2 lone pairs of electrons, still the lone pair on the central sulfur, and then this sulfur is now unchanged. This sulfur has a happy octet in the middle because it has 3 bonds around it, so 6 electrons from the 3 bonds, then this lone pair here. So all of these atoms in this structure as well also have happy octets, and again, we've used up all the valence electrons. These structures are viable. They are in resonance with one another to describe the 2 possible Lewis dot structures for disulfur monoxide. And so again, really looking for a double bond, moving the lone pair into form a double bond, making sure we use up all the valence electrons, no more and no less, and checking that each of our atoms has a happy octet. We use those main facts about resonance that we're familiar with now to figure out that yes, disulfur monoxide has two viable resonance structures. Two Lewis dot structures definitely work for disulfur monoxide. So there's this structure where the double bond is between the central sulfur and then the oxygen, and then this sulfur as well, where the double bond is between the two sulfurs now. These two are just reoriented slightly from what I drew. So I drew the oxygen on the left, and then in the final answer here, it's drawn on the right. There are example 9.7 and 9.8 for more examples of resonance structures. If you want to work through any of those, definitely let me know. Next, we're going to do just a few examples of Lewis dot structures where the atoms have some exceptions to the octet rule. So some exceptions to the octet rule include an incomplete octet. For example, for beryllium and hydrogen, beryllium has 3 valence electrons. Hydrogen has 1 valence electron times 2 hydrogens, that's 2. So this text here describes BeH2. With only 4 valence electrons, we can start to draw the skeleton for this compound here. We'll put the beryllium atom in the middle because hydrogens will not be in the middle. So we only have 4 valence electrons to work with. Have we already used up those 4 valence electrons? Well, yes, right? 1, 2, 3, 4. This is the complete structure. We've used all the electrons we can. Beryllium is satisfied and it's okay with an incomplete octet. This is really the best structure for this compound. Let's look at one more example now with boron and fluorine. So for boron, it has 3 valence electrons. Fluorine has 7 valence electrons as a halogen. So the 21 valence electrons from the 3 fluorines, then plus the 3 valence electrons from boron, that's 24 valence electrons to work with. And putting the least electronegative atom in the middle, we would draw a skeleton like this. So B in the middle, F has to be on the end, just like hydrogen. It only wants to form 1 bond. Because fluorines are coming in with 7 valence electrons already, they only need to bond with 1 other atom to then have a happy octet. Those 7 valence electrons on fluorine, by the way, just to picture them more easily, it's this one that it's sharing with boron, then 2, 3, 4, 5, 6, 7. Those are the 7 valence electrons around fluorine, and then it's bonding with boron. So then it's sharing another electron to then have a happy octet with 8 valence electrons around this atom. So there's 3 lone pairs of electrons here around this fluorine. So with 3 lone pairs in a bond, all the fluorines now have happy octets. We've used all the valence electrons because 1, 2, 3, 4, 5, 6. Then 18 electrons remaining, where those 18 electrons, there's 6 of them on each of the fluorines. So 1, 2, 3 lone pairs around fluorine, that's 6 electrons, 6 electrons, and 6 electrons. We've used up all the valence electrons, we have no more, but does boron have a happy octet? Well, 1, 2, 3, 4, 5, 6 valence electrons around it. This is also now the best structure for this compound. Boron is okay with an incomplete octet. So some of these central atoms here are okay with an incomplete octet. This is the best structure that can be drawn. This is the most stable form of this compound. Then we can even see some weirder exceptions to the octet rule, so even like odd electron molecules. For this compound of N and O, nitrogen has 5 valence electrons, oxygen has 6 valence electrons. We have 11 electrons to work with. We would start to draw N and O as the skeleton. Now we've used up 2 electrons in that bond. Oxygen is to the right of nitrogen. Oxygen is then more electronegative than nitrogen. So to start to add these electrons to the more electronegative atom, which would be oxygen, so 1, 2, 3, 4, 5, 6, 7, 8, it now has a happy octet. Now we have 3 electrons left. What do we do with those 3? I guess try to put them around the nitrogen. Does nitrogen now have a happy octet? 1, 2, 3, 4, 5. If we pull this double bond in, oxygen still has a happy octet. Nitrogen, instead of just having 5 electrons around it, now in this structure where we've moved over that double bond, it now has 1, 2, 3, 4, 5, 6, 7. 7 electrons around it is better than just 5 electrons around it. It still doesn't have a happy octet. It still has this one odd electron here. So we can again see different exceptions like this as well. Then one more kind of exception. So we saw the incomplete octet, and then we can also have molecules with expanded octets. We'll only see expanded octets when the central atom has a principal quantum number or a value for N that's greater than 2. So for sulfur hexafluoride, sulfur has 6 valence electrons. Each fluorine halogen has 7 valence electrons times 6. That's 42 valence electrons, then plus 6 is 48. 48 electrons is a lot to work with, but if we start to draw the skeleton, we would draw the least electronegative atom in the middle, which is definitely sulfur because fluorine is the most electronegative atom. Then those fluorines also like to be on the end. So we're not going to see 2 fluorines bonded to each other. For example, like this fluorine will never be in the middle. These halogens and hydrogen like to be on the end of a molecule or compound. So 1, 2, 3, 4, 5, 6. Then we need to add on those lone pairs around each of the fluorines. This is the only possible structure for sulfur hexafluoride. Does this sulfur have a happy complete octet? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around the central atom. Sulfur is okay with this idea of an expanded octet. Sulfur can have an expanded octet and still be a stable molecule, or be part of a stable molecule. So we can see some incomplete octets, we could see some odd electron molecules, and we can see some expanded octets as well. Let's just go into a few different examples. So let's do PF5, for example. If you're given PF5 to draw or to think about, let's see what this looks like. Based on phosphorus's placement on the periodic table, it has 5 valence electrons. Fluorine as a halogen has 7 valence electrons. There are 5 of them, so 35 plus the 5 from phosphorus. That's 40 valence electrons to work with for this structure. Phosphorus is similar to sulfur in that it can have an expanded octet. Phosphorus is in the 3rd row or 3rd period, meaning it'll fill N equal 3 shells. That means it has the possibility, has to be N greater than 2 to have an expanded octet. So because it is a period 3 element, it has shells of n equal to 3, phosphorus could be okay with an expanded octet. So if we draw the less electronegative atom in the middle, and then we draw the skeleton around phosphorus, so far I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons of the 40 we had to work with. With 30 electrons remaining, we start to place those around the fluorines. Each of these fluorines can have 6 more valence electrons around it. They still have a happy octet. 1, 2, 3, 4, 5, 6, 7, 8. Fluorine itself does not like to have an expanded octet. It likes to come in with its 7 valence electrons and then bond to one other atom to fill its happy octet. It has a happy octet again because 1, 2, 3, 4, 5, 6, then 7 that it's coming in with. Then it's sharing one more valence electron with this atom that it's in a bond with. How many electrons did we use up by placing 6 valence electrons around each of the 5 fluorine atoms? So that's 6 times 5, that's 30. We've used up all the electrons. This is the stable configuration of phosphorus pentafluoride. So phosphorus is okay with an expanded octet. How many electrons does it have around it right now? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How do we know that phosphorus, like sulfur, is a third period element and therefore it can have an expanded octet? Well, we come back to this rule that the expanded octet can occur if a central atom has a principal quantum number greater than n equal 2. If you look at phosphorus on the periodic table, you'll see it has an atomic number of 15. For neutral phosphorus, it will have 15 protons and then also 15 electrons. To fill 15 electrons and to see that we go into the shell of over n equal 2, we're going to fill 1s2, 2s2, 2p6. That's 10 electrons so far. We have 5 more. What energy level comes after 2p6? What subshell? That is 3s. 3s can hold 2 electrons. Now we have 3 more. After 3s, we go into 3p. With 3 more electrons, that must be 3p3. Do we see n levels or shell levels greater than n equal 2? Well, yes, we definitely do, right? Because n equal 3 and n equal 3 here for phosphorus. So because phosphorus can fill a shell of n greater than 2, it's filling n equal to 3. It can possibly have an expanded octet, so that's why this structure does work. So to check what's happening here, we did check that each of these fluorines has a complete octet. Then the phosphorus in the middle, we saw it has 10 valence electrons around it. It definitely has an expanded octet, but that's okay because it has an n value greater than 2. It fills shells where n is equal to 3. So phosphorus is okay with an expanded octet. Let's try drawing just one more together. So here, SO4 2-. Do you remember the name of this from earlier in the semester? This is a sulfate ion. We're told in the description that all 4 oxygen atoms are bonded to the central sulfur atom. I also wanted to go through this one because this one has resonance and it's an exception to the octet rule. So for SO4 2-, we should figure out how many valence electrons we're working with, and we have that 2-, meaning we'll have 2 additional electrons beyond the valence electrons supplied by sulfur and oxygen. So sulfur has 6 valence electrons. Oxygen also has 6 valence electrons. There are 4 of them. 6 times 4 is 24. 6 plus 24, that's 30, but now we have 2 additional electrons because we have an anion. Anions are negatively charged. They have gained 1 or more additional electrons. So 30 from just sulfur and oxygen plus 2 more is 32. Sulfur is less electronegative than oxygen, so we put it in the middle, then put the 4 oxygens around sulfur. We were also given that hint here in which all 4 oxygen atoms are bonded to the central sulfur atom. So if we're dealing with a more complex structure like this, you would expect to see a hint to help you draw a certain Lewis dot structure. So with this hint that's given to us, we do know that all 4 oxygen atoms will be drawn around the central sulfur. Sulfur is also less electronegative than oxygen, so it makes sense that it's the central atom. And so we already counted the number of valence electrons. We have 32. If we're drawing this skeleton of a structure like this, then at this point we've used up 1, 2, 3, 4, 5, 6, 7, 8 electrons just from drawing in those bonds. With 24 electrons remaining, we draw those on the outer atoms. The outer atoms are the more electronegative atoms. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. We're not disobeying the octet rule for oxygen because these still have 1, 2, 3, 4, 5, 6, 7, 8 electrons around each oxygen atom. Drawing 6 around the 4 oxygen atoms. Now we have used up these 24 electrons because 6 and then times 4, that's all 24 electrons. So the oxygens all have happy complete octets, and the middle sulfur, what about that? It has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it as well. So technically this one looks okay because they all have happy complete octets. We learned about something in the previous part of chapter 9 that could impact, though, how we think about this structure. Is this a good structure for this molecule? Well, before we say that, we should check the formal charges. What are we looking for with formal charges? We're looking for all the atoms to have as close to 0 of a formal charge as possible. +1 can be okay, -1 can be okay. We saw that -2 is not good, +2 is not good. So ideally, all the atoms have formal charges of 0. When dealing with a polyatomic anion, we also know that the formal charges need to add up. The formal charges on all the atoms need to add up to the charge on the ion. In this case, all the formal charges need to add up to -2. Let's figure out the formal charges, see if this is accurate, then decide should we try to draw resonance or not. Let's look at the formal charge on sulfur. It wants to have 6 valence electrons. It has 0 non-bonding electrons, or 0 lone pairs. Then -1/2 times the number of electrons in the bonds around sulfur. There's 1, 2, 3, 4, 5, 6, 7, 8 electrons within bonds around sulfur. 6 minus 4, that's a +2 formal charge on sulfur. Uh-oh, that's not an ideal formal charge. Then each of the oxygens look the same, so if we find the formal charge on one of these oxygens, it will be the same for the others. Oxygen is coming in with 6 valence electrons based on its placement in the periodic table. Then the number of electrons that are lone pairs, 1, 2, 3, 4, 5, 6. Then minus 1/2 times the number of electrons in a bond around oxygen. There's one bond from oxygen that contains 2 electrons, so we put in 2 here. 6 minus 6 is 0, minus 1 then, 0 minus 1, that's -1. That's okay. So that means at this point, every oxygen has a -1 formal charge, and then our central sulfur has a +2 formal charge. Not ideal for the sulfur, but let's see if these all sum up to be -2 for a SO4 2- anion. -1 plus -1 plus -1 plus -1 for the 4 oxygens, then +2 for sulfur. -4 plus 2, that does at least total up to the correct charge we expect to see on a sulfate ion. So SO4 2-, at least the formal charges do add up to -2, but this probably isn't the best structure because a +2 formal charge is not ideal. Let's see if we can rearrange some of these lone pairs into double bonds and see if we can minimize this formal charge on sulfur. So here are those formal charges we figured out: -1, -1, -1, -1, and +2. This is not the ideal Lewis dot structure because of that 2+ formal charge. Sulfur is right next to phosphorus on the periodic table, so it will also fill shells of n equal to 3. Because its shell number can be greater than 2, it is greater than 2, sulfur could be okay with an expanded octet. Let's try moving in at least one lone pair in to form a double bond. So now let's see what the formal charge would be on sulfur with one double bond going to it. Sulfur has 6 valence electrons. Still in the structure, it has no electrons that are in lone pairs. Then -1/2 times the number of electrons in bonds is 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9, 10. 6 minus 5 is a +1 formal charge. +1 formal charge is more ideal than +2. But can we make the formal charge even better? Can we make it a 0 formal charge? Well, let's try moving in yet another lone pair of electrons into a double bond and check and see what the formal charge is then. So now, as drawn, it definitely has an expanded octet, but that's okay because it does fill a shell greater than 2. So sulfur could be okay with an expanded octet. Let's check its formal charge. 6 valence electrons minus 0 electrons in lone pairs minus 1/2 times now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons in bonds around that central sulfur. 6 minus 6, we have achieved a 0 formal charge. The formal charges on these oxygens here with a single bond and 3 lone pairs, those are still -1. Did we help or hinder the formal charges on these oxygens, though, that now have a double bond to sulfur? If we made the formal charges worse, then we need to check that. So oxygen with the double bond, let's get the formal charge. Oxygen has 6 valence electrons. The number of electrons in lone pairs, that's 4. Then -1/2 times the number of electrons in bonds, that's 1, 2, 3, 4. 6 minus 4 is 2 minus 2. Oh, we've actually made it better for these oxygens as well. These all have 0 formal charges too, so this is a really good structure for sulfate. As a reminder from where we started with, it was -1, -1, -1, and -1, and then +2 for sulfur. And so we figured those out here on this slide. Now, by moving in 2 lone pairs into form double bonds to sulfur, now the central sulfur has a formal charge of 0. These oxygens with double bonds also have formal charges of 0. Do all the formal charges still sum up to 2 minus because we're dealing with a sulfate ion of SO4 2 minus? Well, 0, 0, and 0, and then -1 and -1. Yes, that does total up to a charge of -2. This is a great structure because we've minimized the formal charges, we've used up all the electrons, so we've used the correct number of electrons. The octets for oxygen are good, and then the expanded octet for sulfur, that's also okay to do because again, it fills a shell greater than n equal to 2. So for n greater than 2, yes, it goes into n equal 3. Sulfur can have an expanded octet, so this is okay. And so to clear this out now, to show it a little bit clearer, this is in possible resonance in how I drew double bonds going in this direction too. So the 2 double bonds don't necessarily have to be on the oxygens that are up and down from the sulfur. They could be on the top and to the right. They could be on the left and on the bottom. The key here is to have the central sulfur, then 2 double bonds to the oxygens. Then for the other 2 oxygens, just single bonds. So you may be wondering the question of which of the structures is more important? The one in which sulfur obeys the octet rule but bears a more formal charge of that +2? Or is it the one where sulfur has an expanded octet and then it has a 0 formal charge? Well, it turns out this is a little bit up for debate, which is pretty interesting. The key concepts here that are important is looking at how to calculate formal charge and being comfortable drawing possible resonance structures where we've drawn in that lone pair in to form a double bond. This one is not necessarily so much worse than this one, but for this one, the takeaways would be that, okay, we did achieve a 0 formal charge on sulfur, and we practiced drawing resonance by taking in a lone pair of electrons in to form a double bond. Within those formal charges too, we needed all the atoms' individual formal charges to total up to -2 for the charge on this polyatomic anion. So it's not necessarily, again, that this one is so much worse. It's looking at the key concepts we just went through to predict this one. Resonance and formal charges are what we focused on in this example. And so if we had taken all of the lone pairs we could into forming double bonds, what ends up happening for an incorrect structure like this is we end up with a -2 formal charge on sulfur. We don't want a negative formal charge on sulfur because sulfur is less electronegative. Sulfur is less electronegative than oxygen. That means that sulfur does not want the negative formal charge. You don't want to put a negative formal charge on the atom that is less electronegative. So you might think, well, what if we had done that? Well, this is why this is not a good structure. We don't want a negative formal charge on the atom that is less electronegative. And so for some additional exception examples, you can check out 9.9 and 9.12. With any problems you want to talk through, definitely let me know. For drawing Lewis dot structures, the focus should be on drawing the non-exception Lewis dot structures. In order to feel comfortable drawing exceptions, you would expect to have some hints like this and like this in order to draw a Lewis structure with exceptions. So focus on the non-exceptions for drawing Lewis dot structures. And so be sure to practice with drawing those. The more you practice, hopefully the more comfortable you'll become with drawing different Lewis dot structures. I'm going to include one animation on resonance. As always, with any questions, definitely let me know. And I hope you're all doing well, and I will talk to you next time. Now for chapter 10. So keep me posted if I can help with anything, and I will talk to you all soon. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Consider the Lewis structure of ozone O3. We satisfy the octet rule on the central oxygen by placing a double bond between it and one of the two end oxygen atoms. The molecular geometry of ozone is bent or V-shaped. If this were the correct structure of ozone, we would expect the oxygen-oxygen single bond to be longer than the oxygen-oxygen double bond. We would also expect a greater electron density in the region of the double bond. An electrostatic potential map of ozone with one single and one double bond is shown. The electron distribution varies according to the colors of a rainbow. The most electron-rich region is red. The most electron-poor region is blue. Experimental evidence, however, shows that both oxygen-to-oxygen bonds are equal in length at 128 picometers. We resolve this discrepancy by drawing a second Lewis structure with the double bond on the other side of the molecule. Each of these structures is a resonance structure, which is one of two or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. The double-headed arrow indicates that the structures are resonance structures. A common misconception about resonance is the notion that a molecule such as ozone somehow shifts quickly back and forth from one resonance structure to the other. Keep in mind that neither resonance structure adequately represents the actual molecule, which has its own unique stable structure. Resonance is a human invention designed to address the limitations of a simple bonding model. The correct electrostatic potential map of ozone shows that the electron density is evenly distributed between the two end oxygen atoms. This indicates that the two oxygen-to-oxygen bonds are of equal length and strength.